Okay, so today is Wednesday, September 23rd, and we're doing map estimation with quadratic priors. And, oh, I forgot to get the notes out. So last time, I think I feel like I kind of did some tangential stuff a little bit last time, but I don't remember exactly what I did. But, okay, so basically what happens is this. Okay, 4. What happens is this, that, so the concept in map estimation is that the negative log of P of y given x. So that's the forward model, right? And it's equal to 1/2 y minus ax norm squared. If this is true, and plus some constant. If this is true, what's the noise variance in the model? The noise variance. So let me write this over here. Hold on. You can tell everybody really loves that thing over there. It slowly has made its way to the corner of the room. Okay, don't turn me in, okay? I'm innocent. Oh, why? Oh no, I'm not innocent because it's on film. Okay, never mind. Okay, there. Okay. Oh, okay. I'm sorry. Okay. Okay, so that's the forward model. That's the model. Okay. And this thing is distributed as RW. Okay. Right? Actually, what we're going to usually use here is we're going to use this notation. So that's the inverse covariance, so it's a precision matrix for the noise. And usually, what's going to end up happening, not always, but usually this thing is going to be like a diagonal matrix, okay? So it's going to be a diagonal matrix of like lambda, so it's going to be, and its entries will be like 1 over sigma 1 squared. Actually, let me just do it like this. It'll be like W, yeah, I'll make it like this. Okay. In other words, these will be the inverse covariance of the noise. So in the simplest case, which we do, I kind of add complexity as the notes go along. I start with the simple case, so you get the intuition. And then I add more bells and whistles, right? So the simplest case is that lambda equals, say, 1 over sigma squared I. So it's just, that would be the noise variance. But it might be that the noise for each measurement is different. That's a pretty, that's not an uncommon situation. Actually, one of the applications of all this is what's called computed tomography, CT, okay? And in CT, you have like a source of X-rays, okay? So this is a motor, okay, that spins a tungsten disc, okay? And over here, you have this thing is a oh, okay. I'm an electrical engineer, and I'm going to end up getting this wrong. electrons are negatively charged, right? So if you have an electric field, they're going to go in the opposite direction of the electric field, correct? Okay, right. So it's like this. So this might be, you know, I don't know, 100 kilovolts, okay? This is a high voltage source. And electrons come off of here. So this is like a light bulb, okay? Like if you have the filament in a light bulb, you get it very hot. So the purpose of this current isn't for the electricity itself, it's just to make the thing hot. And then when it gets hot, electrons come off of it and they accelerate, okay? And then you have some kind of focusing mechanism. So the electrons accelerate and then they hit this target, okay? And when they hit the target, you get X-rays, okay? And you'd say, well, why do they have a motor attached to this? They have a motor because if they don't spin that, the electron beam will just drill a hole through the thing, okay? So they have to do that in order to get an intense enough X-ray source. So the X-rays come out, and then they go through this, and then there's a detector, okay? And you measure it. Okay? Actually, the detector actually has a thing in front of it called a scintillator. You can't actually measure X-ray photons directly, at least not with conventional devices like CMOS sensor that you have in your phone, because the X-ray photon will just go right through it. It doesn't stop it. So you have to put something in front of the sensor that has enough stopping power for the X-rays. And when it hits that, it's called a scintillator. It hits it, and it either creates light, or it creates electrons, or something that it hit the detector, and then you get a measurement, right? So there's actually two kinds of, I'm getting off on a tangent here, but I think it's all useful things to know. There's two kinds of detectors. There's photon counting detectors and there's integrating detectors. A photon counting detector, the signal that comes out of here, you'll be like, and that's the event, right? So then you have some kind of threshold, and when it exceeds the threshold, you declare an event occurred, and then you report back some information. Usually the integral of this thing, you may report back some information, or you may just report a binary event, okay? But to do that is complicated, because what'll end up happening is if you have multiple events that occur, if the flux is too high, you'll have multiple overlapping events. So then you can't do that, because it'll get, I mean, theoretically, I guess you could try to separate them, but it's really hard. And remember, this is running at gigahertz rates. So after the event occurs, there'll be some sort of dead time, usually, in which, because you have to have some decision logic, and it can only run so fast. Even if it runs in a nanosecond, you have a nanosecond of dead time. So the alternative approach is that you just let them all go for it, okay? And you just get a bunch of junk out there, okay? So it all integrates together, and you get a total signal. That's the conventional thing you would do with a CCD detector or CMOS detector. It's an integrating detector as opposed to a photon counting detector. Then what ends up happening is the signal you get is proportional to a weighted sum of the photons, because some photons have more energy than others. So the total signal is not just proportional to the number of photons, it's also proportional to their energy, perhaps, or something else. You know, usually the energy. Because remember, and what's the energy of a photon proportional to?
Constant times frequency.
A constant times the frequency. And what's the name of that constant? No, close, but completely wrong. Planck's constant. Thank you. Yes, Planck's constant. Planck's constant is like the speed of light in that it's a universal constant, right? that determines the relationship between frequency and energy, okay? By the way, there was some kind of recent thing, oh shoot. Oh, it's all mixed up in my brain, but there was a recent thing that occurred where they finally, they keep boiling, the international bodies that define standards keep boiling things down to more and more basic things, right? At one time they had like a piece of gold somewhere that in a vacuum that everybody kind of looked at, that where they had like 2 etched lines, and that was the international definition of a meter, okay? But that's obviously pretty sloppy, right? So they keep doing more and more sophisticated things. So I think it's now defined in terms of the number of wavelengths of some atomic oscillation frequency, okay? So the thing they can do most precisely is define a oscillator, okay? Because they have very ultra precise oscillators, right? That's how they can measure time very precisely. So then Planck's constant relates time to basically time to energy, and energy is related to mass through C. So if you can define time very accurately and Planck's constant very accurately, then you get mass and energy units. And they recently adopted a shift in the thing. I wish I could remember it more precisely. I'll go look up the video where they were, they're boiling it down to simpler and simpler things, right? And more fundamental. That was a little tangential. But anyway, so you have a scintillator here, okay, right. So then this measures this, okay? The point is, now if you have an object, let's say this is a hunk of metal or a piece of bone, the X-ray doesn't penetrate that as well as it does something else, maybe plastic or soft tissue. So some of your measurements are going to be much noisier than others. They're not all the same. In the limit, if this is super dense, you just can't get anything through it, right? So not all measurements are the same. Some measurements, the other possibility is that your material might be so undense, I don't know what the reverse of dense is, that you can't see the thing because it doesn't absorb anything. So that would be like, they have these, I think these materials that are called the lightest materials ever created or something like that. They're called, what are they called? Alessandro, you probably know. Aerogels, thank you. They're called aerogels. And they're like super, 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 super light, right? And they're just really, you can look them up. So if you want to image an aerogel, the problem is you get no absorption is the problem. So then effectively the signal-to-noise ratio may be lower in some sense, right? So my point is just that not all measurements are the same. Some measurements are more reliable than others. So, but in this case, the measurements are all independent. They're independent. You'd say, well, they're not independent because the object is the same. They're all measuring the same object, so they're not independent. Well, yeah, that's sort of true, but it's really, that's not what I mean by independent. What I really mean is they're conditionally independent, conditioned on the object. So the conditional probability of the measurements given the object, those are independent. So it's equal to the product over I equals 1 to m, if there are m measurements, of the probabilities of I of yi given x, okay? So they're conditionally independent. Okay? So that's what happens here. These measurements of y given x are conditionally independent. But they're not independent because they depend on x in a Bayesian framework. Now, they're conditionally independent, but that doesn't mean that So this noise here may be, the elements of this vector may be independent, but that doesn't mean that they're white. White means that, and it doesn't mean they're IID. It doesn't mean they all have the same distribution. They're all Gaussian, but they don't all have the, and they're all zero mean, but they're not all the same variance. They may be different variances, okay? So that's the conditional, so this is it. So in this case, what's the conditional variance of y given x? What's the conditional variance of each element of y given x? If I write this log likelihood down. Excuse me? Yes, that's true. But by looking at this expression, can I tell what R of W must be? So this is, I've actually written here, so the thing here is that, like, you have to get good at, or it's good to get good at, these are like Rubik's Cubes, right? You have these moves you can make, right? And it's like a deductive system, right? So you can do this, you can do this, and you have to figure out which moves are useful, right? But you also want to kind of get good at them, so you just automatically can see the moves that you can make, okay? It's like playing chess or something like that, or checkers. So I can go from this model to this model, but I can also go from this model to this model. So you should be able to look at this at some point and be able to look at this and say, oh, what does that tell me about what this model's form should be, okay? So from this, okay, so if I know that this is the forward model, then what's the conditional log likelihood have to be? Well, this thing is going to have to be, can I write that down? So I want to do this, okay? Help me do it. What should it be? First of all, excuse me?
There should be like a 1 over something.
Okay, so it's got to be a 1 over something, okay? Now let's assume that y here is a member of r to the m. So in other words, we have m measurements. Okay, so then what's the 1 over thing going to be?
2 pi.
So it's going to be a 2 pi. Yeah, m over 2, okay? Now what? Is it off? We got off to a good start.
Times the,
You don't have to do everything all at once, so do the easy part first. It's always better to try to do the easy part first and fill in the harder part as you go along, right? So it doesn't have to be in order. You know that there's a thing in there. There's a functional in here. There's a function in here. It's got to be here, right?
exponentials.
You got to have an exponential. So I'll put that there, okay?
It's going to be a 1/2.
You got to have a minus 1/2, correct?
-1.
So go for the easy stuff first. We're engineers. We don't have to have any pride, okay? We just do the easy stuff first, okay? Pride goes before the fall, as they say. Okay, what's next? So it's going to have to be what? There's going to have to be a covariance in here or something, right? And there's going to have to be a mean, right? Now, under normal circumstances, you would have y minus the mean transpose r inverse y minus the mean, correct? So then the question is, well, what's the mean going to be? This isn't actually the mean.
It's going to be the expected value of y and x.
Yes, this is the conditional mean. So one of the things that you should come out of this class having learned, hopefully, is the idea. I mean, you won't learn everything. There's a lot of material here, okay? But one thing you should really come away with an appreciation of is conditional probability distributions, okay? Which are really important and not very well understood by the broad technical community, really. This is not going to, mu here is not the mean, it's the conditional mean. It's the conditional mean of y given what? X. So what's the conditional mean of y given x? AX. So this is going to be y minus AX, correct?
Yep.
And then I have to have y minus AX here too, right? Does everybody follow that? You know, when I get up here and I do this stuff because I do it all the time, so it's super automatic for me, right? But it's not super automatic for you yet. So I want to make sure I do it. So I can do it. If I do it and you go, oh yeah, that's right. Okay, you didn't pay any attention to me. Okay. Then if I do it slowly, it's like, you know, it reminds me of this. It's like somebody who speaks a different language, right? And you go, hi, what are you doing today? And they look at you and they have no idea what you're saying. And you say, hi, what are you doing? Like if you speak slowly, it doesn't help because they don't know what you're saying, right? It's silly, okay? It's just dumb. So if I go slowly, it doesn't necessarily help, okay? What I have to do is you have to really fully be driving it, okay? And then once you go through it once, it'll make sense and it'll set in your brain. So now what's this thing? It's the conditional covariance. So what's the conditional covariance of y given x? It's going to be, I'm hearing a lot of good things, but it's going to be this lambda inverse. The key idea is this. The conditional variance of y given x is the variance of w, is the covariance of w. Because w is independent, right? If I didn't have a w here, the conditional variance of y given x, y would be certain. There would be no uncertainty in y. The uncertainty in y would be with nothing, okay? I'd know exactly what y is. Y would be ax. I'd be done. But there's some uncertainty in y because I added w. So the uncertainty in y is exactly the uncertainty in w. I mean, that's the intuition. Of course, you can prove it mathematically. So this thing here is going to be what? It's going to be this lambda it's going to be actually lambda.
Yeah.
Because it's R inverse.
Yeah.
Okay? You got that? Now we can come over here. What's this? We have to finish it up. So the way I never know the answers to this question, including right now. So I have to always figure it out every time. Okay? Maybe you guys are better. Well, you guys are probably better than I am. Okay? But the point is that even if you're handicapped like I am, okay, and you can't remember anything, you can always figure it out again. Okay? So let's see. I know it has to be something involving lambda. Okay? Now there's two possibilities, and I can remember, even I can remember that there's a 1/2 involved, okay? So there's a 1/2, and that makes sense because I have to take the square root. See, the thing is that this was scalar. Why do I have this here? I have it here because if I increase the variance, then the sig spreads out. But the integral has to remain 1. So if I spread it out, I have to divide by a bigger number so the integral remains 1, correct? So I can't divide by sigma squared because that would be the wrong scaling. I have to divide by sigma, okay? So I have to take a square root. Because when I take this has got to be a determinant. Because I have to take the square root in the scalar case, so that works so I take a square root. Now the question is, do I multiply or divide? Well, the elements of this lambda are 1 over sigma squared. So here I just multiply. So that's the answer. All right? I didn't really need all that detail because when I take the log, this just becomes a constant because it's not a function of x. So that's where I get this. except for this is wrong, okay, because I haven't finished it. If I take y minus ax transpose times lambda times y minus ax, that's a lot to keep writing, and I have to keep writing y minus ax more times than I'd please. So I have a shorthand notation for that. And the shorthand notation is what? I use a norm. So I use the norm of y minus ax, a norm squared, because this looks like a norm squared, and then I subscript it by lambda. And that's definitionally true. That's just the meaning of this notation. Okay? So then I just put a lambda here and I get that. And if you wanted me to compute exactly what C is, I could do it. I just have to take the log of this thing over here. Okay? So everybody's got that? Because we're going to do this many times. Are there any questions about this? Because getting these like really simple basic things right is really the most important thing in this class. Because that way you can use these techniques, right? Okay, now, and then the prior model is log of p of x. And what's that going to be? We're assuming it's a Gaussian Markov random field, right? So what's minus log of p of x? So what should that look like? It should be a quadratic form. And so it'll look like what? What's the first term here? Make me feel good and tell me. It's a 1/2, okay. And then what? It's an x transpose, then what? Bx. I mean, it doesn't have to be b, but I use the letter b usually here, right? And then plus a constant, but it's a different constant, right? All right? And now, I'm going to erase this here, okay? And then, what is the form of B? If the matrix is, if you, let's say you have a circulant, it's a circulant matrix so that you don't have to worry about the boundaries. And it's homogeneous model, non-causal predictor, then what's the form of B? Do you remember?
Are you looking for a Topol's block, or are you looking for symmetric?
I'm looking for circulant. Circulant's a special case of toplets. Yeah, so it's space invariant. So it's going to look like, well, what's the form? B has, the diagonal entries of B are what? Excuse me? Yeah, so it's 1 over sigma non-causal squared, right? And then what's the matrix? The I, it's I minus G. So G is the predictor, okay? And here G is going to be a symmetric matrix if it's, we're assuming J is circulant, so it has to be symmetric in that case, okay? So you get the intuition? In 1D, this thing would look like 1 over sigma it would look like it has 1s on the diagonal, say in 1D, okay? And here it would have like minus rho over 2, say, minus rho over 2. That would be like in the case of just having, order P, what I said. So you'd just be predicting each pixel from its 2 neighbors in 1D, okay? And if it's a circulant, then it also has to be minus rho over 2 here and minus rho over 2 here, but that's kind of a detail. That circulant thing just takes care of the boundaries. Why do we use circulant matrices? Is it because they model the physical world particularly well most of the time? No, because most things in the world are not circulant, okay? Circulant would mean that like the left hand right of the side of the board and the right hand match. Well, probably not. Maybe, sometimes, but usually not. If it's a tile flooring, of course this is cheap tile, so it doesn't match anyway. But like if you had good tile, it would match, okay? Right? So why do we use circulant if it doesn't really model the world all the time? Excuse me? Because of the fast Fourier transform. And also because, well, yeah, basically because of the fast Fourier transform means that we can get analytical solutions to problems, closed form, okay? Which is normally you can't because the eigenvalues for the matrix are going to be complicated. But in the special case of circulant, they're simple. What are the eigenvalues of the matrix if the matrix is circulant? Can you find the eigenvalues of a matrix if it's circulant? It's just the DFT of what? The DFT of what? What do you take the DFT of? Let me ask you this. What does circulant matrix represent? It represents convolution. So what would you take the DFT of? Excuse me? Could you say it one more time?
The DFT of the signal.
Yeah, of the signal, of the impulse response, right? And how do you find the impulse response in the matrix? You look at like a row or column of the matrix, right? If it's a circulant matrix, what does it mean for a matrix to be circulant? It means that Bij, or we'll say Gij, is equal to Gi minus J mod n, okay? So this function G is the thing you take the FFT of. So how do you recover G from the matrix? Well, you look at one of its rows. The row, what'll end up happening is like, this will be G0, this will be G1, and this would be n minus 1, okay? And then it's a circulant function. So you just take the FFT of that, okay? I know these are like a lot of simple ideas, each of which is like sort of simple, but maybe not completely simple. And then they go by you really fast, and then I say them, and you nod, and then by the time you're finished, you can't remember anything, okay? So, but I think the key here is it's like if somebody was teaching you to play chess, and you said, now how does a rook move? I don't understand, okay? And you said, well, you go 2 forward and 3 across, or 3 forward or 2 across, or 3 back and 2 across, and you'd be like, I'm confused, okay? But really, it's not that complicated how a rook moves once you get the idea, but you have to remember it, okay? And you have to remember how all the pieces move, and then you can start combining the moves together to play chess, okay? So that's what these are. These are like the moves you have to be able to make to play this game, okay? So let's just go over it one more time. So this is a forward model. Maybe I'll start erasing some extra junk. Here, I can erase this, right? I'll erase this. I'll erase everything that we really don't need. Okay, let's go through it now. This is our model. It says that our observations are a linear transform of the unknown plus some noise. The noise covariance is assumed to be, the noise precision matrix is assumed to be this lambda, okay? So RW equals lambda inverse, okay? If lambda is a diagonal matrix, taking its inverse is very simple, okay? You just take the inverse of each element. By the way, if a covariance matrix is diagonal, what does that tell you about the elements of the vector, of the random vector? If the covariance matrix is diagonal, what does that tell you about the associated random vector? Its elements are independent, right? Or at least uncorrelated, correct? Everybody remembers that? Okay. So with that model, this is the forward model, okay? The conditional distribution of y given x. The negative log likelihood looks like this, okay? So, and the negative log likelihood of the prior looks like that. And b here is equal to what? It's 1 over sigma squared times what? Times I minus what? And what is G? It's like the circulant non-causal prediction matrix, okay? And if a matrix is circulate, can you compute its eigenvalues? And how do you do that? You use the FFT. Okay, good. You're all rock stars, okay? Now, okay, good. Now let's go back and just look at this a little bit more. No, let me write one more thing down, and then we'll... Now, if I compute the map estimate, what does map stand for? Yes. That's equal to the arg min over x of what? The negative log of p of y given x minus the negative log of p of x, right? Okay? So that's equal to what? If we plug this in, this is the arg min over x of what? Yeah.
Plus C if you want to be specific.
Is that good? I just substituted those two things in. Why did I drop C prime and C?
Because you're taking it with respect to x, so those are just constants.
Yeah, because this is acting for the, if I had arg, then I have to keep the C. But if I have arg min, if I min, I could drop the C. I could have to keep the C. I keep saying everything wrong, so I don't know how you could possibly learn anything, okay? Okay. If I had min, I'd have to keep the C, because it would be saying, if I raise the entire North American continent by 5 feet, then it changes the answer to the question, what is the minimum altitude in the United States, okay? But if I ask, where does the minimum altitude, if I ask what is the minimum altitude in the United States, it changes that answer. If I raise the entire North American continent by 3 feet, because that answer has to increase by 3, okay? But if I ask where does it occur, it doesn't change the answer. It's still Death Valley, right? So the argument is not affected by any constant you add. Right? So I can drop the constants, correct? What does this term mean intuitively? If I'm trying, let's say that this, I'm going to write this back in, so don't worry, I'm not messing up your notes. If I just did that, what would happen? What would I be doing? What's the solution? And let me even do this. Let me just get rid of the lambda for now, because it just makes things more complicated. So if I minimize this, what am I doing if I'm doing that? If I do that, What do we call that? There's a name for this.
Maximum likelihood.
Yes, it's maximum likelihood for sure. What else is it called more conventionally outside of this classroom? It's called the least square solution, right? It's the least square solution. It's like what you learn to do when you're doing plots. You do a least squares fit. That's the least square solution. It's exactly the same thing. When you're doing the plot, if you're doing like a linear plot, then this A actually has two columns to it, one associated with a constant and one associated with the line. You might also do a polynomial fit, okay? The solution in that case is what? In that case, x hat ml is what? It actually turns out to be A transpose A inverse A transpose Y. Right? Okay, that's the least squares fit. Actually, if A transpose A may not be invertible, in which case you have to take the pseudo inverse, okay? All right, but what is that? That means you just fitting X to the data. The solution may actually be non-unique. If it's the reason you have to do the pseudo inverse is because the solution may be non-unique, in which case the pseudo inverse gives you the solution with minimum norm, actually, okay? So then, but then you have this other term here. What's this other term doing? Well, B, remember, X transpose BX. Basically, when I use the word basically, it means everything I say after that is true, okay? Because I'm giving myself some wiggle room, okay? Basically, what you're doing is this. You're taking XS times XS minus the sum over R, neighbor of S, of B, actually this is GSR, I guess I would make it S minus R, times XR, like that. That's what that's computing. This thing here is the difference. If your prediction error, this thing is the prediction error. If the prediction error is 0, okay, then this thing will be 0. The point is this. This thing is a penalty, a smoothness penalty. It's a penalty on the thing being unsmooth, okay? This is a smoothness. I should actually put unsmoothness penalty. By the way, I want to also point out that we'll later learn that in 1D, this is exactly the same thing as solving what's called Laplace's equation. How many people are familiar with Laplace's equation? Okay? Laplace's equation is the equation you solve in order to find like an electromagnetic field, or also if you have like a thin membrane, like a bubble, okay? So if you have 2 points and you pull the rope taut, the solution is that the rope goes straight, right? But if you have a deflecting force, then the rope might go this, okay? So this Laplace's equation is exactly this thing. So this is a penalty that penalizes like basically variations in the signal, okay? So this thing is saying fit data. This thing is fit the data. This thing is be smooth. So you want a smooth resolution that also fits the data. The prior encourages smoothness. The forward model term encourages it to fit the data, okay? Yeah?
What would be an example of smoothness for a line? I mean, since it's a line, is the line going to be smooth all the time? So.
If it's straight, there's some issues here in the way I drew this. I'm misleading you a little bit on purpose. So let me do something that's a little more precise, okay? So let's say you have, this is n, okay? And this is, so xn, right? So now you have some function. So is that smooth? Well, maybe not, okay?
We can't get that function with our model. Doesn't py given x tell us that has to be a line because we have this a?
Py of x.
It has to be a linear function, or no? Like,
I'm a little confused, but you said something about.
Like this y minus ax says.
Oh, this.
Our model's linear, and then now you're saying we also want to make it smooth. And now my question is like, what does it mean to have a smooth line?
It's an excellent question.
Okay.
The thing that's smooth here, this is this is asking for x to be smooth.
Oh, like the vector inside of x.
Yeah, it's not even that. The problem is that, okay, the linear thing here is the mapping between x and y. Mm-hmm. But that doesn't mean x has to be smooth. When you do a least squares fit, x here would be the actual parameters of the least squares fit. In that case, making them smooth would seem to be a bizarre thing, okay? Because they don't represent, they're not spatially ordered. Like those would be like the coefficients of the polynomial, okay? There's things you could definitely do there. There you would use a technique called lasso, which I bet you're familiar with, because you're, which we'll talk about actually. But here, but in that case, this covariance matrix wouldn't be homogeneous. It wouldn't be circulant. It would be diagonal. But anyway, so the model's linear, the forward model's linear, but that doesn't mean that that x, the solution to it, has to be smooth. So let me show you this result again from before, because I did the problem exactly like this, okay? In chapter, hold on. So I can show you the example again. Here. That's exactly this, okay? So here, actually the model was linear because actually in this example, A was I, it was the identity. So it's linear, right? That's the original signal. That's the signal with noise. But the covariance estimate here, B here, was, but this estimate, right, is not smooth.
I see. So
right?
With respect to the indices within x, so like x at 0 and x at index 1 need to be close or something?
Exactly.
Okay.
Now here, okay, exactly. Everything I tell you, unfortunately, is a lie, okay? Okay, but there's, in my friend's term, well, okay, there's some truthiness to it, you might say, okay? So, I kind of progressively reduce the amount of lying I do to you, okay? And hopefully we converge towards something which is more truthful, okay? So, with that thought, what did you just say? I can't, that it has to be more smooth. In some application, you might know that, in fact, every other value has to be exactly reversed or something, right? So it doesn't, the more general concept is not that it's necessarily smooth. I'm using the word smooth because that makes you feel good, right? Because physical phenomena tend to be smooth, right? At least as you get to a high enough resolution. So, but more generally, it has to obey some prior distribution. And that, usually the prior distribution has some enforcement of smoothness. But one person's smoothness can be another person's roughness, right? Oh, we're out of time. So in other words, my idea of smooth might be like this. Okay? So it can, maybe I can have, I'm like, it has to be smooth, but it could have jump discontinuities. Or it might be like, my idea of smooth might be like this. You know? Yes, no, yes, no. It's very predictable, okay? So it's not smooth, but it's very predictable, okay? So smoothness is a general idea, and it's embodied broadly by saying I have a distribution, okay? Okay, and the concept, okay, since I have you here, and I gotta let you go now for sure, because I'm really running over. I'll just show you one more picture, because this is like part of my brainwashing strategy. Okay. Okay, let me just show you this picture that you thought, oh, he's really losing his mind, but this is important, okay? It basically says most of the space is empty. That's the key idea. Most of the space is empty. So if most of the space is empty, I can make my problem much simpler by getting rid of all the stuff I know can't happen. But you have to be a little careful, because you might throw the baby out with the bathwater, okay? So with that thought, read the notes, okay?